right, this is from the textbook's 10.36. Determine the electron group arrangement, molecular shape, and ideal bond angle for CO3 2-. So of course, the first step is going to be for us to draw the Lewis structure. And again, since this is a multi-step process, we do again need to be thinking about each of the steps to ensure that we're doing this correctly and accurately. Because if we mess up the Lewis structure, there's a very solid chance that we mess up other parts of this along the way. So I'm going to start up here because I know I'm going to need some more room for this. I'm going to start by placing my atoms relative to one another with the least electronegative in the center. Then I'm going to calculate my valence electrons. Carbon has 4, oxygen has 6, giving me a total of 22. But because I have a negative charge, I'm going to add 2 more. I will have a total of 24 valence electrons. I can place now my single bonds, from the surrounding atoms to the central atom. I'm going to adjust my valence electrons, 2, 4, 6. So 24 minus 6 is going to take me to 18. And now I can place my valence electrons. 6 on each oxygen, 3 lone pairs, and 3 times 6 is 18, so then I have officially used all my valence electrons. Now we need to double check and make sure that everyone has their octet fulfilled. My oxygen has 2, 4, 6, 8. Since all 3 of my oxygen are identical, oxygen is all set. However, when I look at carbon, I can see that carbon only has 2, 4, 6 valence electrons. It does not have an octet. And that means that I need to go to step 5. I'm going to take a lone pair from one of my oxygen and form a double bond, which is why I've left myself all this nice room down here. So my new Lewis structure is going to look like this. One, 2, 3, 4, 2, 4, 2. All right, now let's double check our valence electrons. I have 2, 4, 6, 8. 24 minus 8 is going to be 16. 2, 4, 6, 8, 10, 12, 14, 16. All of my valence electrons are accounted for. Everyone now has an octet. Carbon has 2, 4, 6, 8 involved in bonding. This oxygen has 2, 4 in bonding, 2, 4 in lone pairs, octet. And then the other 2 have the same structure as in our initial Lewis structure. So everyone has an octet. Am I finished? No. Because this is a polyatomic ion, I need to include my square brackets and my charge. All right, now I have completed step 1. Step 2 is to identify and assign my electron group arrangement for this molecule. So to do that, I need to look at my central atom, which is in this case carbon. Carbon has how many bonding and non-bonding pairs? It has 0 non-bonding, and it has 2, 4, 6, 8 electrons. So 1, 2, 3, 4. And it has 4 bonding pairs. However, this is where we get our, I'm going to make a note of this, bonding pairs. However, as we have these 2 isolated electron groups, this is where the distinction between bonding pair and electron group is very, very important. We have we have single bonds that are each acting as a bonding group on these 2 oxygen. However, this single oxygen is involved in a double bond, meaning there are 4 electrons in that space. However, if you think way back to when we introduced VSEPR theory, when we were talking about bonding or electron groups, This is an example where multiple bonds, so multiple electrons, more than 2 electrons, are acting as a bonding group. So we have 4 bonding pairs, but we have 3 bonding groups. So again, it's very important to distinguish between bonding pair and electron group. So this is 3 electron groups. When we have 3 electron groups around our central atom, that indicates what electron group arrangement? Yes, it is trigonal planar. So now that we have identified our electron group arrangement, in step 3, we can move on and now that we have our electron group arrangement assignment, we can talk about our ideal bond angle. When we have trigonal planar electron group arrangements, our ideal bond angle, because all 3 of those surrounding atoms are in the same plane as the central atom, the ideal bond angle is going to be 120 degrees. However, we do need to consider the fact that we have a double bond. When we have a double bond, is that going to increase, decrease, or not affect the bond angle experienced by the other 2 surrounding atoms? Because of the increased electron density in the double bond, there is going to be a decrease in the bond angle between these 2 oxygen. So our ideal bond angle is 120 degrees. However, due to the fact that we have a double bond, we are going to have an actual bond angle of less than 120 degrees. I promise that says actual. We have a bond angle, an actual bond angle of less than 120 degrees. All right, finally, step 4 is going to be to draw our molecular shape and name it. So again, we're going to place our atoms relative to one another, starting with our carbon, oxygen, oxygen, oxygen. And since this is a trigonal planar molecule, we are not going to need to use our perspective wedges. We're not going to need to use dashed or solid wedges because all 3 of these are in the same plane, remember. And I apologize, that is not a great straight line. There we go. That looks more like a solid line. So we have our carbon and our 3 oxygens bonded. We do need to include our valence electrons. And now that we have drawn our molecule with accurate shape, we can name it. We have 3 bonding pair, or 3 electron groups around our central atom. So our central atom A, 3 bonding pairs means that this is going to be what molecular shape? It is going to be trigonal planar as well. All right, and there you have it. That is one example. We'll go through another one. All right, so for this practice problem, I will identify each step for you, and then what I would like you to do is pause the video, work through that step, press play, and then take a look at the answer for each step, or the solution for each step. And then this way you'll get a little bit more practice internalizing the steps and working through them on your own. So let's start with step 1. We are looking for the Lewis structure for SO2. So pause the video, draw the Lewis structure for SO2, and then check back. So for step 1, I hope that this is your Lewis structure. Hopefully you figured out that when we do our initial Lewis structure, we end up with an insufficient number of electrons for our central atom. So we need to donate an electron pair, and we end up with an oxygen double bonded to the sulfur, single bonded to an oxygen. So step 2 is to determine our electron group arrangement. Go ahead, take a look at your molecule, take a look at the number of electron groups, and assign an electron group arrangement. So for step 3, you should have trigonal pyramidal. Again, we have 3 electron groups. We have 1 lone pair, 1 single bond, and 1 double bond. Remember, those multiple bonds count as 1 electron group. So because we have 3 electron groups around our central atom, we have a trigonal planar electron group arrangement. Step 3 is to determine our ideal bond angle, and in this case, remember to look for things like single pairs and double bonds and determine how they will affect the ideal bond angle. So the ideal bond angle for a trigonal pyramidal electron group arrangement is going to be 120 degrees. But because we have a lone pair that's repelling a double bond, the bond angle between the double bond and the single bond is actually going to be less than 120 degrees due to that increased repulsion between the lone pair and the double bond. Now, step 4 is to draw our molecule shape and then name our molecular shape. So our molecular shape is the bent molecular shape because we have a VSEPR shape class of AX sub 2E. And we've got 2 bonding groups and then 1 lone group, which means that we're going to have 1 lone pair, which is going to contribute to the bent shape. And again, you don't have to use a protractor or anything, but this is going to be a bond angle of less than 120 degrees due to the repulsion between these two and the even greater. So because we have a lone pair, that's going to kind of push away a single bond even more than it's going to push away the double bond. But also because it has such a strong repulsion, it's going to cause an even smaller bond angle here. And there you have it. Part 2 of problem 1036.